So our next speaker is Ioannis Papadimitriou, who will tell us about algebraically special holography. Take it away.
Great. Thank you very much. Thank you also to the organizers for the opportunities. It's not. Sorry? It's not working? Who's working?
Yep.
It is working, right?
I suspect the battery is running out.
And they will both
Try this one. That's the noise I think. Otherwise, you can use something.
Okay, sorry. Okay. So, yeah, I was saying I would like to thank the organizer for giving me this opportunity to present this work. So this is work with in progress with Kostas Kenderis that is actually kind of a follow-up of some very old work of ours, like on black hole ADS black hole thermodynamics. So we thought that we kind of understand, like, I mean, a very large class of, like, thermodynamics for a very large class of ADS black holes, but there have to be some kind of, there were some kind of a puzzles, like, I mean, in recent years that we were trying to understand. So, and that's the origin of this work. So let me just, like, give you the motivation of this. So the motivation is some kind of recurring problem that has appeared, like, in thermodynamics in general, not just in ADS, but also, like, in other asymptotic spaces. So it has to do with the way one goes about computing the thermodynamics in probably the simplest way. So usually we have some solutions that depend on a number of parameters, and then we compute in one way or another, we compute the thermodynamic variables, like, as a function of these parameters. And then to demonstrate the first law of the black hole thermodynamics, we usually take the variations, like, with respect of the conserved or the thermodynamic variables with respect to these parameters. And now the puzzle arises that in some times, like, I mean, this first law here, like, this kind of relation doesn't seem to hold, right? I mean, which is kind of contrary to what you would expect. And so there are some concrete examples of this issue. So the ones I'm going to like refer to in this talk are what they're going to be related to the problem I want to solve. So a first kind of example of this is like just standard care ADS5 black hole. And then there are also black holes in anti-de Sitter space with scalar hair, like certain kind of scalar hair that I'm going to mention in a little bit. And then the problem that, like, I mean, kind of I want to address, like, I mean, now is this accelerating ADS black holes. Right, so now the kind of a overview of the general approach, like, I mean, that, like seems to resolve this type of problem is when you look carefully at the variational problem, right? I mean, so you have some kind of gravitational action, and the boundary terms and the variational problem that, like, this action satisfies is very important, like, I mean, in order to have a well-defined thermodynamics. So in particular, what I mean by a well-defined variational problem is that you need a number of ingredients, so you need a configuration space within which to take the variations. You need boundary conditions and associated boundary terms that impose these boundary conditions. And of course, in the context of the ADS-CFT correspondence, there is a corresponding, like, all these ingredients, they have some kind of dual, like, meaning. So let me not go into the details of this dual description, but let me just kind of go very quickly through these examples that I mentioned earlier, because they're going to be important later. So the first one is like this KR-ADS5 black hole that I mentioned, and then like in this audience, probably everybody knows that, like, I mean, when we look at the asymptotic solutions in anti-de Sitter space, then we have a conformal boundary instead of a normal boundary, and that means that basically the bulk fields induce like a conformal equivalence class of boundary fields, boundary metric in this particular case. So then when we're talking about boundary conditions, it doesn't really make sense to keep the conformal representative fix, which is the boundary metric, but rather the conformal equivalence class. So that means that, like, if I write it in terms of a formula here, so I need to put like the kind of standard, like most appropriate boundary condition for anti-de Sitter space would be like this conformal Dirichlet boundary condition, where I allow for this Weyl transformation of the boundary metric. So here, on top of that, I'm allowed to have like some boundary diffeomorphism. And this is clear now that like leads like, to a well-posed variational problem thanks to the word dentist like of the dual field theory, which is of course consequence of the Bulk-Einstein equations in holography. So in particular here, if I plug in this type of variation in this variational problem, then I just get 0 by virtue of this two-word dentist. Of course, this is now an assumption here. I'm just saying in terms of the dual field theory, I'm saying that the conformal anomaly is 0, which is, of course, not always the case. So, and that was the original, like the caveat when people looked at the thermodynamics of the KRADS5 black hole. So in that case, so let me just say first generically, so if that's not the case, so if the conformal anomaly is numerically non-zero, then these boundary conditions that I wrote before give you this kind of variation, so it's a non-zero variation, and that's not a well-posed variational problem. So only in that case, when there is a non-zero conformal anomaly, then one has to impose a stricter class of boundary conditions, which is actually the strict Dirichlet boundary conditions, well, up to boundary differs. So in that case, you cannot use conformal Dirichlet, you have to impose this stricter condition. Now, the problem with the KRADS5 black hole is that the boundary metric itself depends on the parameters. So it depends on the rotation parameters. So if you apply the naive variation of the parameters, which is what I mentioned in the beginning that we use to compute like the variation of the concept of the thermodynamic variables, then the boundary metric changes. And then you can show that in the KRADS5 black hole with two rotation parameters, you can show that this is the variation of the boundary metric with respect to the rotation parameters takes this form with a non-zero Weil parameter here. So this kind of violates the consistent boundary conditions in that case because you have a non-zero anomaly. So the resolution in that case is that basically you need to compensate the total variation with respect to the parameters with a bulk DFO that induces a boundary Weil, so that basically you do impose the correct boundary condition. And once you do that, then everything works fine, including the Casimir energy here, which let me not go into the discussion here, but it's also, this point is very crucial also in order to have the correct Casimir energy. Okay, so now let me mention the second example that is also relevant for the subsequent discussion, is when we have, again, ADS black holes, but with scalar here. And then in particular, this is relevant in the case where the mass of the ADS scalar is in that window where you have both modes being normalizable, so you can have like kind of all different types of boundary conditions. So then there are certain classes of black holes that they satisfy this kind of relations between the two modes. So this is the subleading mode, and this phi minus is the leading mode in the asymptotic expansion. So, and there are certain black holes, like usually in ADS4, but not only, that satisfy this kind of relation where alpha is some constant that is parameter of the solution as well. So now, when we have this kind of relation between the modes, then clearly this boundary condition is not standard Dirichlet, it's what we call mixed or like Robin boundary condition. So this means that in order to implement this boundary condition at the level of the variational problem, you have to add an appropriate term that keeps like this J, which J now corresponds to this particular combination, fixed, right? So if you don't add this boundary term, so that, I mean, the variational problem gives you this expression here, then you're going to end up with the wrong thermodynamics. You're not going to recover the thermodynamics. So, and in that case, like, I mean, on top of this boundary term, you also need to keep fixed like this parameter alpha that is part of the definition of the boundary condition. So if you do that, then again, you can show, as it was shown in this paper here, that like the thermodynamics work perfectly. And this is in contrast to some claims like in the literature that you need to add scalar charges, like, I mean, in addition, like to recover the first law. So although there was no conserved charge associated with the scalar charges. Okay, so now let me come to the main problem that I want to address, which is the thermodynamics of accelerating black holes. So again, these black holes are within the general class of asymptotically locally ADS solutions. So in principle, they should be included in the previous discussion. However, now in this case, I'm talking about ADS4, so there's no conformal anomaly in the dual three-dimensional conformal field theory. However, the puzzle here is that if you take the variation of the boundary metric with respect to the parameters, you get something which is not of that form, right? I mean, so it contains some other piece that is not of that form. So clearly this violates the most general acceptable boundary conditions that I mentioned before for asymptotically locally ADS black holes. So, and resolving this is kind of a puzzle. Like this is the goal of this work. And so this observation here is related to the fact that also the thermodynamics doesn't seem to be working, like, or have some special and a little bit strange properties. So the thermodynamics of accelerated black holes have been studied in several papers, like in recent years. So the punchline is that somehow you need to kind of make rescalings, like, of the time coordinate in a particular way, or like restrict the number of parameters, like, impose some kind of relation among the parameters in order to get a well-defined variational, like, thermodynamics. But, like, all this seem kind of artificial, and there is no good explanation of why, you should impose these kind of conditions. Now, the possible resolutions of this, like, based on the previous discussion, is that we can, so assuming that the issue is, like, with the variational problem, which I claim it is, then there are two possible resolutions to this problem. So the first is that somehow we have to impose, like, mixed boundary conditions. So in the case of gravity, that means, like, that we impose some relation between the stress tensor of the dual CFT and the metric of the boundary theory. So that's one possibility. So in particular, like, there would be some relation, like, between the cotton tensor and the stress tensor. So there are examples of these kind of relations. For example, like, when you have like solutions that are self-dual, like, with respect, so the Bile tensor in the bulk is like is dual or anti-dual. And there's a second option, which is we impose, like, some generalized Dirichlet boundary conditions. And these would correspond to the existence of an additional non-relativistic word identity, such that although this variation is not of the form that I wrote before, this variation is still zero. Okay, so now both Candace resolutions rely on the existence of the special property of the dual stress tensor and the background metric. So it doesn't hold, like, this kind of generalized boundary conditions that I mentioned, they have to rely on some special properties of the stress tensor, right? So they cannot apply to all asymptotically locally ADS solutions. So that motivates us to look, like, for a broader class than just accelerating black holes, but large enough in order to be able to formulate the variational problem, like, in a meaningful way. And this is the class of algebraically special solutions in ADS for gravity. And the most common example of that is the so-called Robinson-Trautmann class that corresponds to the non-rotating version. So I'm going to mention, like, more about these solutions, like, in a moment. So these solutions, they provide a suitable configuration space for formulating the variational problem for accelerated black holes. So the accelerated black holes are a special case of these algebraically special solutions. And if a well-posed variational problem is formulated, then we can go beyond the thermodynamics, because then we can build a holographic dictionary based on the variational problem. So let me just go through now, like, first describing the algebraically special solutions, and before go to accelerating black holes, and then the holographic description. Now, the most general algebraically special solutions of Einstein's equations are exact solutions that possess, like, null geodesic congruence with vanishing shear, and mostly they are known in 4 dimensions. So there are several examples, like, also in other dimensions, but these tend to be very restrictive. Like, the best known examples are in 4 dimensions. Now, again, the most common one is the Robinson-Trautmann solution that is non-rotating, or it has, like, zero twist, and they are solutions of Einstein's equation. So solution is maybe a little bit of misnomer, because they don't solve exactly the Einstein equations. They solve exactly the radial dependence of the Einstein equations, and they are subject to transverse constraints. And this is analogous to pure ADS3 gravity. So in that case, again, we have the exact form of the radial dependence of the solution of ADS for general asymptotically locally ADS solutions. But there are transverse constraints, like, on the CFT stress tensor, right? So this is very analogous to this case. The difference here is that now the solutions in the bulk are not conformally flat. And the same is true for the boundary metric. So maybe I'm not going to go through the technical details of that. So this is, like, the line element here for the Robinson-Trautmann solution, the non-rotating one. And again, like, all the radial dependence is determined here, apart from this transverse equation here, like, for this, conformal factor here, and this Laplacian here on the Riemann surface. So this is the so-called Robinson-Trautmann equation. And so the solution has some properties, like for example, like it has a curvature singularity like at r equals 0, like generically if this mass parameter is non-zero. And then this equation here describes what is known as a Calabi flow. So this Robinson-Trautmann equation, which is the transverse equation, describes what is known as a Calabi flow. And this can be generalized like for higher dimensional Hermitian like Kähler manifolds. And now the important here observation is that like this Calabi flow, it has been shown that like if you start with any kind of spherical topology, like I mean if the base, like the Riemann surface is of spherical topology, and you evolve this, the metric like under this Robinson-Trautmann equation, you always end up like in this fixed point here, which corresponds to the ADS Schwarzschild black hole, like in Eddington-Finkelstein coordinates. So it has been shown that the late time behavior of the solution of the Robinson-Trautmann equation, and therefore the Robinson-Trautmann solutions, is basically the ADS Schwarzschild. Of course, this changes if you have like different topology, like cylindrical topology or something like that. So how much time do I have? Thanks. Okay, so maybe I skip like some of these details. So the origin here of these algebraically special solutions is the fluctuations around the Schwarzschild black hole. So it was an observation by Regge and Wheeler originally that you can factorize the Schrödinger equation that corresponds to the fluctuations of linear perturbations around the Schwarzschild black hole. And there are special modes that saturate like that are zero under one of the two factors here. And they correspond to, so you can write the Hamiltonian like in this form here. And then solutions that are annihilated by one of these supercharges, like fake supercharges, are correspond to these algebraically special solutions. So they satisfy this kind of fake BPS equation here. So it's a first order equation, and then the corresponding frequencies are algebraic, so they are given by this expression, and that's why they were originally coined algebraically special. Now, and here the relation to the Robinson-Trautmann equation is that now if you look at perturbations of the Robinson-Trautmann equation now, not the four-dimensional equation, Einstein's equation, if you look at perturbations around the Schwarzschild ADS solution, so this particular phi 0 that I wrote the fixed point before, this solution here, if you look for perturbations around that, then you find these perturbations and that are characterized by exactly the same frequencies. So from both sides, basically, then you conclude that somehow the nonlinear algebraically special solutions, the Robinson-Trautmann solution in this case, is a nonlinear description of these special algebraically special fluctuations of perturbations of the Schwarzschild black hole. Now, there is a more general class of algebraically special solutions that was originally written down by Timofeev in '96, I believe. So this is is not very well-known solution, I believe. Like there are very few papers that mention this, and this is the rotating version of the algebraically special solution. So it has a non-zero twist. So the twist is related to this field here, sigma, that is some curvature like based on these functions L. So it's not important the details of the form of the solution, but again, the important thing is that it solves exactly the radial dependence of Einstein's equations, and then there are, sorry about this, there are again a number of transverse constraints that one needs to solve in order to complete the solution of Einstein equations. So the constraints here are this, and then there is, the first one here is it's a complex constraint, so the complex conjugate gives an independent condition. Now, so let me go into the accelerating black holes now. So the accelerating black holes are known since very long time ago, so almost since the advent of general relativity. so in the form of the symmetric that was mentioned earlier today. And this is the non-rotating version of the accelerating black holes, and then it has been generalized, by adding several parameters. So the most general solution is the so-called Plebansky-Damiansky solution, and in the Petrov classification is a type D solution. So generically, it includes cosmological constant, acceleration, mass, rotation, not parameters. And the important thing for us is the fact that this general class is contained within the Timofeyev solution, this algebraically special solution that I wrote, and because this Timofeyev solution contains all the Petrov type D solutions. And again, there are generalizations of all these solutions, to Einstein-Maxwell theory, and in certain cases, to gauge or ungauge supergravity. So here is the non-rotating version of the accelerating black hole with no zero knot parameter. So again, in these coordinates, so this Boyer-Lindquist type of coordinates, the conformal boundary is at h going to 0. And so for non-zero mass, again, mass parameter, again, there is a Kermatov singularity, at rho going to infinity. And in the special feature of these solutions is that if this combination here is non-zero, then there is always a conical singularity, on the horizon. So let me just show the diagram instead. So here, this is a conical singularity that you can arrange to be either at the North Pole or at the South Pole entirely, but you cannot eliminate both conical singularities. So this can be interpreted as a cosmic string going all the way to the boundary, so that's pulling the center of the black hole. Okay, so now let me go very quickly through the holographic description of, or the attempt to the holographic description of the solutions. So here is just a very brief summary of the dictionary for generic asymptotically locally ADS solutions. So the asymptotic, the form of the solution is this. So this is the boundary metric, and this G3 here, this coefficient, is the stress tensor and satisfies these constraints. Now, for the case of algebraically special solutions, for the general class now, for the Timofeyev solution, not just the Robinson-Trautmann one, we can perform the holographic analysis and derive now the holographic data. So the boundary metric takes this particular form here, and I can write this in terms of some choice of a dry bind, some basis of vectors basically here. And now the stress tensor has a very special and important form. So you can write the stress tensor in terms of this form here that is like a conformal fluid stress tensor, but there is some extra contribution here that is related to the cotton tensor of the boundary metric. And this is necessary in order for the stress tensor to be covariantly conserved. Right, so now the same thing should happen for the accelerating black holes, and this is kind of highly non-trivial, because if you just do the holographic calculation for the accelerating black holes, especially the rotating one, then, well, the boundary metric is already complicated, and then if you do the same analysis for the stress tensor, you find something very complicated that is not obvious what are the properties of that. But again, there is a very special basis again of field binds such that it takes this form. So it had to be the case because, again, it's a special case of algebraically special solutions. So the metric, the stress tensor had to be of that form. So we just had to find the appropriate basis, of field binds in order to write the metric, the stress tensor in that form. Right, so we have now the stress tensor again in that form. So in both cases, both accelerating in the more general algebraically special solution, we have the general form of the stress tensor. And then now, maybe I skip this. So this is just the general, so this form of the stress tensor form falls in the general class of conformal fluids in 2+1 dimensions, but there is some special form of this term here. Now, this stress tensor here that algebraically special and therefore also the accelerated black hole satisfy is of this form here, so it satisfies this constraint. Now, this is the main result so far, of this analysis, that basically there is a constraint in the form of the stress tensor, in the form of the stress tensor in terms of the cotton tensor. So some components are related among the two. And this constraint is non-relativistic necessarily. So here, this IJ, these indices are here Lorentz indices. So now this constraint here can be interpreted in two ways, either as a mixed boundary condition or as a word density for the stress tensor, and this leads to two different choices of boundary conditions. So, so in the first case, we would require to add the boundary term, in order to impose this mixed boundary condition. So here we have looked extensively for some kind of gravitational Chern-Simons, non-relativistic gravitational Chern-Simons, but so far we haven't succeeded in producing the exact form of this term. But this would be, it's still a possibility that exists, such a boundary term. The second possibility is generalized Dirichlet boundary conditions, which is basically that we allow for a different, for an additional type of variation of this boundary metric beyond Weil and Diffeo. And nevertheless, because of the special form of the stress tensor, this is still the case. So, and indeed, this we have confirmed that the general class of accelerating black holes, including rotation, indeed falls precisely into this category. So we have shown exactly that this holds, even without the integral, so that you can write the variation with respect to the parameters in exactly that form. Okay, so let me conclude. So first of all, black hole thermodynamics are related to a well-posed variational problem in general, so at least that's what we have learned from experience so far. Now, algebraic special solutions provide a suitable configuration space for formulating the thermodynamics of accelerated black holes. And accelerating ADS4 black holes are compatible with the general Dirichlet boundary condition thanks to the existence of an extra non-relativistic word density. So that's what we've shown. So, and this leads to well-defined thermodynamics in that case. But what we hope, for subsequent analysis is that we can actually use this variational problem in order to study things beyond thermodynamics. So study holography, for algebraically special solutions. Thank you for your attention.
So you wrote down the very general metric for algebraically special solutions, which includes all Petrov type D solutions. Is that proven even in the presence of matter?
This one, right?
Yes.
Yeah, so if this metric is valid in the presence of matter?
So if the solutions, so if we subject this metric to the Einstein equations, if the corresponding solutions are going to be even in the presence of matter, algebraically special?
So this is a solution of vacuum Einstein equation with a negative cosmological constant. Actually, you can turn on or off the cosmological constant. There are different versions. But there are versions of this for Einstein-Maxwell theory. Okay. So, but it changes.
But not for general matter.
For general matter, I'm not aware of.
Okay, thank you.
Sure.
Any other questions?
That this extra worded non-relativistic word identity, what does it relate to on the boundary?
So on the boundary, it just corresponds to this relation for the stress tensor. So, this is the most compact way that you can write this word density. So this T here is the Tij, is the stress tensor, but in a field-bind basis. So Ij are local frame indices. And so this is just the the time-like component. And this Cij K here is the cotton tensor of the boundary metric. So this relation here is a relation between the boundary stress tensor and the cotton tensor, which is a function of the boundary metric. So it just gives me some particular relation. So this is the most compact way that one can write it. I can write in terms of some projectors, but that's a formality. So now the physical interpretation of that, the only thing I can say right now is that it corresponds to the fact that the stress tensor takes this conformal fluid form, but conformal fluid is generalized on a non-conformally flat manifold. So it reflects this, right? So this constraint that I wrote down is it's a kind of it's a property of this type of stress tensor. So physically, what I would say is that the stress tensor has to have this kind of conformal fluid form, even though the background is not conformally flat. Now, it generates a symmetry, which like is what gives me a well-defined bidirectional problem, the word density. So this symmetry, like, I mean, I cannot tell at the moment much. So this is what we are studying at the moment. Please.
Maybe remains, but it looks like some kind of deformed trace. Sorry. It looks like some deformed trace, right? Some kind of scaling symmetry that's different in one direction and another direction.
That's right. That's right. It's not a scalar, right? I mean, because it's I mean, this condition here has like 3 indices, right? I mean, so it's not a scalar constraint. It's stronger than that, but yeah, it's non-relativistic for sure. Yes.
Thanks.
Any final question?
Are there any higher dimensional algebraically special solutions that you might want to apply these techniques to?
Yeah, so that's a good question, and I mentioned in the beginning that like there are known algebraically special solutions in other dimensions.
Right.
But first of all, there are different definitions of algebraically special that in 4 dimensions they coincide, but in different dimensions, like, and then they become inequivalent.
I see.
So, and then, yeah, depending on which definition you follow, then, I mean, you get different results. But the generic property is that always they are much more constrained. So you don't have all these arbitrary functions that you have like in 4 dimensions. So 4 dimensions seems to be special with respect to that. But yeah, there are like, at least there are some versions of algebraically special for certain other dimensions.
I see.
There's a paper by Harvey Real, like, I mean, from around 2010 or something like that, that
Right.
discusses this extensively.
Okay, thanks.
Let's thank Ioannis for the nice talk.